In this video, we'll begin our discussion of the sum and difference identities. These identities, these two, I'm just going to give you, there is a way to derive this, but I'm going to save video time by not deriving our sum and difference identities, but we'll use these identities to prove other identities. All right, so my first part, we have these two formulas. Notice what it is it's cosine of the sum of two angles or the difference of two angles. So if the two angles are being added inside my cosine, I can split them up to be cosine of the first one times cosine of the second one minus sine of the first one, sine of the second one. Same thing on the second. Notice, though, the difference between the two is we started with a plus and had a minus. And then on the other one, we started with a minus and ended up with a plus. You do not need to memorize these. It's a good thing to know them. If you can get them into memory, that's fantastic, of course. But you won't be expected to be able to write them down out of nowhere. But being familiar enough that way you can recognize it without a reminder in the future is your goal. Okay, so find the exact value. Notice this one's set up just like our formula. So we'll be able to just straight up use it. Okay, this one is this formula. It's the minus. So I'm just going to fill in each angle. So it's cosine of the first angle times cosine of the second angle. And then since it was a minus, this is going to be a plus. Sine of the first angle times sine of the second angle. Okay, and then we just evaluate all these. These are unit circle values. If they weren't unit circle, we would just use our calculator. Cosine of pi over 3 is 1/2. Cosine of pi over 2 is radical 2 over 2. Plus sine of pi over 3 is radical 3 over 2. And then sine of pi over 4 is radical 2 over 2. These are just unit circle values. I expect that you have these down at this point. So now we're multiplying this as radical 2 over 4. And then radical 6 over 4. And we can add those together to make it a little simpler if we would like. Radical 2 plus radical 6 over 4. That's our exact answer. We could stop. If you want a decimal, plug that in. Just be careful that these are in parentheses or that you're using some kind of fraction option on your calculator. Right, what these normally, where these become powerful, one in theory, because I can use these to prove things, and we're going to do that towards the end of this lesson. I'm doing some identities. But what's nice is notice that cosine of 105 degrees, if we think about our unit circle in degrees, 105 is not on my unit circle. So what we can do is manipulate this, though, and call this cosine of, and I'm looking for something in my unit circle. So how I do this is I just pick one I know. So I could pick 30 degrees. Well, if I pick 30 degrees, that's going to leave an angle of 75 degrees. While 30 is on my unit circle, 75 is not. All right, so we're going to try something else. 30 wasn't on there, so we try 45 degrees. If I take 45 away from that, I get 60. And that gives me two angles that are actually on the unit circle. Okay, I'm going to do 60 degrees plus 45. And hopefully, some of you guys may have noticed this already, forgive me, that this 60-degree angle is actually just pi over 3. This 45-degree angle is just pi over 4. So I could write this out. Cosine of 60 degrees. Make sure you put your degree symbol. Cosine of 40 degrees, 45 degrees, sorry. And then since it was a plus, this is a minus. So sine of 60 degrees and sine of 45 degrees. So I ran out of room there. But when I multiplied, that's the exact same thing. All this was going to end up there. It's the same angles. It's going to hit the same ratio. So this is equal to square root of 2 plus the square root of 6 over 4. So you're just looking for two angles that maybe will add to that. All right. So let's take a look now. We'll do sine as well. I was going to say part 2, but I'm going to go ahead and do it all in one. So part 2 would be our sine, no longer part 2, this is part 1. Of our sine angles, notice that they are very similar. The only difference here is, notice it does sine, cosine in each one. It flips them. And then it also keeps the same sign, so plus and plus. And then it also does, okay, so sine of A, sine of B, beta. Sine of alpha, sine of beta. And then we also, in cosine, have cosine of beta, cosine of alpha. So it does the sine of both and the cosine of both, and then keeps the sign in between. All right, so let's look at number 1 here. Number 1 is sine of 45 degrees minus 30 degrees. And we're just going to plug it in. Sine of 45. Oh, first let's make sure we're using the right one. We're going to use the bottom one because there's a minus. So sine of 45 degrees times cosine of 30. Let me shrink this up a bit because I'm going to need to write. Fit it in, I mean. Alright, so we have cosine of 45 degrees and sine of 30 degrees. Right, now we just evaluate all those. Sine of 45 degrees is radical 2 over 2. Cosine of 30 degrees, that's my small triangle, so it's radical 3 over 2 because cosine is x. Minus cosine of 45 degrees, which is radical 2 over 2. And then sine of 30, all right, that's going to be 1/2. Wait, no, it's 30 degrees. Yeah, it's my small triangle. There we go. So I get radical 6 over 4 minus radical 2 over 4. And that's going to be similar to my answer earlier, just with a minus. So these are, if we pick them up from our unit circle, these type of answers, this radical 6 and 2 over 4 stuff, becomes very common, as long as the angles are from my unit circle. All right, so number 2, we have sine of 135 degrees minus 120 degrees. And I use that same formula. This is going to be sine, oops, bad S there. Sine of 135 times cosine of 120 degrees minus cosine of 135 degrees times sine of 120 degrees. Make sure that you get cosine of both and sine of both, and then the sign between stays the same. Okay, 135 degrees. My brain doesn't work in degrees, so I'm going to go ahead and convert 135. So I'm going to take 135 degrees, and I'm going to multiply by pi over 180. Oops, let me get back to that. All right, so I got 135 divided by 180. And then I'm going to change it back to a fraction. So I got 3/4. This is the same thing as 3 pi over 4. Okay, so that helps me. I just think in radians. That's because I'm a calculus professor. Okay, 3 pi over 4. That is the second quadrant, and we're thinking sine, so it's going to be positive, and this is just going to be a radical 2 over 2. Cosine of 120. Okay, 120, that is 30 more than 90. So this is a third, so it's going to be 2 pi over 3. You could also convert like we just did here to get to that answer. Okay, so we have cosine of 120 then, which is just 2 pi over 3. Okay, so that's in quadrant 2, and we're talking about the x, so it's going to be negative 1/2. Minus, okay, now cosine of 130, which is just that 3 pi over 4. It's cosine, so it's to the left, so it's negative rad 2 over 2. And then sine of 120, which was the 2 pi over 3, is just going up, and that's my tall triangle, so it's going to be a radical 3 over 2. Okay, this is going to erase some of that. I have like a copyright thing right here. Let me erase it real quick. The only way I can do it is color it with white. All right, so we're going to finish that by multiplying. Okay, so we're multiplying now. That's negative rad 2 over 4 plus rad 6 over 4, which is rad 6 minus rad 2 over 4. So like I said, these answers are very common. Notice this ended up being the same answer, which is pretty interesting. So it will come down to just plugging these in. And again, like I've been pushing all semester, the unit circle is probably one of the most important things that we need to be able to do trig. Okay, so all we have to do for these identities is just use them. The hardest part is going to be like in this example here. You have to find a way to manipulate our angles to make them angles that are on our unit circle. That will be our key. So if you have some kind of radian angle, you're going to have to find an angle that will work for both.